Hi, my name is Rodrigo and I will present the work Advanced Kalman Filter Carrier Tracking Performance Assessment under two Ionospheric Scintillation Models. We are researchers from Aeronautics Institute of Technology, Federal University of Ceará, Polytechnic University of Catalonia, and Lumina Institute of Research, Innovation and Applied Technology. Ionospheric scintillation is a physical phenomenon caused by propagation of electromagnetic waves through a disturbed ionosphere, which is common to occur on low latitude and high latitude regions, high solar activity, post-sunset and midnight periods, and low solar zenith angle, which denotes a seasonal dependency. This phenomenon may cause significant impairments in GNSS signals, LEO satellite communication, and radar signals. To exemplify why ionospheric scintillation may be a problem, we show here two impacts in precise positioning and radar systems. In this first one, we have four figures. Each figures have three plots, and each plot represents respectively the phase residual, the number of available satellites, and the 3D error in meters, with respect with time. So for an example, if we pick Presidente Prudente GNSS receiver station, we have that when scintillation is occurring, for an example, within midnight and 3 a.m., we have that the phase residuals becomes very noisy and the number of available satellites drops significantly. And also, consequently, we have that the 3D error in meters becomes very high. For radar systems, we show here specifically for synthetic aperture radar images, three kind of images, so we can take a look on how ionospheric scintillation distorts the image. The first one is an optical image that we selected from Rio Boyá in Amazon for rainforest. The second one is a pulsar sublook image observed in calm ionospheric conditions. And the third one represents image streaking caused by ionospheric scintillation in SAR images. Understanding the ionosphere dynamics offers means for predicting scintillation events, which enables enhanced accuracy and robustness for precise positioning and augmentation systems, predicting and monitoring disaster occurrences such as earthquakes, volcanic eruptions, and usage of nuclear weapons. And a common way of monitoring ionosphere consists in analyzing GNSS signals. Hence, there is a growing need to develop GNSS receivers that are both robust and capable of providing meaningful data on scintillation effects. Over the past decades, the scientific community has devoted significant efforts to characterize scintillation effects and to improve the phase-locked loop tracking system, which is the weak link between GNSS receivers and understanding the ionosphere. Here are some limitations of previous works on enhanced PLLs. The usage of the corner scintillation model, whose fidelity in representing real scintillation events has been recently put under questioning. Usage of real recorded scintillation events with the trended phase component. Almost complete removal of the refractive component due to propagation through the ionosphere. And there is no guarantee that some of the proposed systems would work in a plug-and-play manner in the place of classical PLLs. And these are the contributions of our work on performance comparison of advanced PLLs algorithms under the CPSSM and the CSM. The CPSSM I didn't say before, but is a new model that is being developed by the Colorado University of Colorado Boulder. And what we provide here is an in-depth behavior analysis of single-frequency Kalman filter-based PLLs with autoregressive models for separating the receiver satellite range dynamics from the scintillation effects. We discussed about the interaction between the integrated random walk model that we refer to as the Wiener model for the range dynamics and the autoregressive model for the scintillation effects. We evaluated the feasibility of employing these approaches on real-life scenarios using a Monte Carlo approach, and the MATLAB source code has been made available at the end of this presentation. We also improved the usability of a phase screen model. For testing the advanced PLL algorithms proposed in the literature, we refactored the MATLAB code of a two-component Power law phase screen model that was recently developed by the University of Colorado Boulder, which we refer to as the Compact Phase Screen Based Scintillation Model, the CPSSM, as I have said before. The Satellite Navigation and Sensing Lab of University of Colorado Boulder has posted a publicly available GitHub repository, and we forked it to our laboratory page, and we worked on it on some features of it to improve the usability. A quick disclaimer is that all authorship credits of the phase screen model framework are reserved to the University of Colorado Boulder researchers. We improved code maintainability and readability. The code is now suitable for simulating scintillation events for the Galileo constellation. We added support for complex receiver dynamics such as drones and airplane flight trajectories. The results of this refactored version have been validated using phase screen theory's spectral functions, and the MATLAB source code has been made available at the end of this presentation also. Before delving in the details of our work, I think it's worthwhile to explain what really are cyclosleeps. There is no consensus in the literature on what is exactly a cyclosleep. However, some recently published papers on the CPSSM have shown that there are two kinds of what is being understood as cyclosleeps. The first one is known as phase transitions. So in this figure here, we can clearly see three plots. The first one represents the carrier phase estimation provided by a PLL that is represented in blue. The second line represents the ionospheric scintillation effects. And the third one would be the refractive effect only of the scintillation. So the green one represents what is being received in Earth, and the black one represents what happens in the ionosphere. In the second plot, we have the difference between the carrier phase estimate and the refractive component, and also the diffractive component. It is what we call the difference between the ionospheric scintillation phase and the refractive effect, the refractive phase component. You can also call it like that. So we can clearly see that the green line, that is the true one, presents several jumps, and these would be the phase transitions. But also the blue one has some ambiguities that happens in the phase that are not caused by ionosphere itself, but rather noise-induced cyclosleeps. So when there's a mismatch between the phase from the ionosphere and the estimated phase, and there's an ambiguity happening, we call it a noise-induced cyclosleeps. That is a signal processing error that comes from noise in the receiver. So the third plot represents the difference between the green line and the blue line in the second plot. Here are some examples of scintillation events simulated using the CSM. So in this figure, we have in the first plot the magnitude of strong and weak scintillation events. The second plot represents the scintillation phase. That would be the phase of the complex field that is modeled by the CSM. And the third plot represents the unwrapped version of the diffractive phase or the scintillation phase. Now for the CPSSM, we have again the magnitude, the diffractive phase, and the unwrapped version of the diffractive phase. And just as a quick disclaimer, we removed the refractive effect so we can compare both of them, because in reality they are not likely, because the CPSSM contains the refractive effects while the CSM does not. This is the autoregressive model fit summary. The first figure shows the optimal model orders, the second one shows the residuals, the third one the residual autocorrelation function, and the fourth one the periodogram versus the autoregressive power spectral density comparison. So we can see that in general the fit was well done because the residuals, despite being high for being showing some peaks for strong scintillation events, it's uncorrelated for both scenarios, and the periodograms and the model PSDs fit well. Now for the CPSSM, we have that the optimal order for weak is 14th, and the optimal order for strong scintillation events is the same as the previous one. The residuals again show some peaks for strong scintillation events, while for weak they are close to zero again. In any way, the residuals shows that the residuals autocorrelation functions shows that they are uncorrelated. And there is a well fit in the period between the periodogram and the AR models PSDs. This is our post-correlation implementation of the Kalman filter PLL. So we have here the post-correlation model of the signal that is being multiplied by a carrier replica. And then the signal passes through a discriminator, that is in the case the Arcus tangent of 4 quadrants. And then it is multiplied by the Kalman gain. And here we have the time update step of the Kalman filter, and here the prediction step. The following variants of the Kalman filter PLL algorithms discussed in the literature were employed in this work. The standard Kalman filter that employs a discrete Wiener model for the carrier phase dynamics, the adaptive Kalman filter that employs also a discrete Wiener model, but is adaptive with respect with the measurement noise covariance matrix, the autoregressive Kalman filter that employs again a Wiener model, but in this case we also employ an autoregressive model for the scintillation diffractive phase effect, the adaptive autoregressive Kalman filter that employs the same as the autoregressive Kalman filter, but we also adapt the measurement noise covariance matrix in each time step. And the adaptive had limited autoregressive Kalman filter. That is a new algorithm proposed by the literature that was not very well studied, and we saw that it was promising, and we decided to study it further in this case, in this work. Here we have an example of the total carrier phase error and the autoregressive model of the carrier phase for a strong scintillation scenario simulated using the CSM and different variances of the discrete Wiener model. The higher the uncertainty of the discrete Wiener model, the shyer the autoregressive model becomes, and more noise-induced cycle slips occurs. In this more realistic scenario, we can infer that it would not be possible to use low values of the variance of the discrete Wiener model, since it would impair the capability of the TPLL to maintain lock, yielding several cycle slips. This work underscored the importance of adopting physics-based ionospheric scintillation models on the evaluation of advanced PLL behaviors. We could assess that the Kalman filter autoregressive PLLs that are specifically designed to cope with ionospheric scintillation suffered performance degradation under realistic scintillation events simulated using the CPSSM due to the refractive phase drift. This indicates that it would not be possible to use them in real systems in a plug-and-play manner, without preprocessing the raw data to remove the refractive phase component. It was possible to evaluate the behavior of the proposed PLLs for different modeled variances of the discrete Wiener model. Future research avenues for real-time scintillation mitigation includes multi-frequency carrier phase tracking algorithms that may help identifying and separating the scintillation effects from the carrier phase measurements, using fully adaptive Kalman filter algorithms such that the state and the measurement covariance matrices adapt themselves in real time, improving robustness and accuracy, near real-time smoothing that may help identifying the scintillation effects, and including non-stationary augmentation models to track the refractive phase component. For offline scintillation monitoring, we could avoid using augmentation models such as the autoregressive model and design an accurate and robust carrier phase tracking algorithm using advanced nonlinear Bayesian estimators such as the particle filter and its variants, and smoothers. After tracking the carrier phase as robust as possible, one may employ batch phase transition solving algorithms, such as batch cycle slip solvers, and after removing the Doppler and other effects, it could also be possible to employ radial backpropagation algorithms using phase screen theory for solving the phase transitions. We acknowledge the financial support from CAPES, INPE, CNPq, European Commission, and FINEP. Feel free to access our available material and connect with us using the QR code below. Thank you very much.